I'm going to talk about putting photonics on silicon, and in particular, doing it reliably, which is the problem because there's a big lattice mismatch. And the second problem I want to address is the lack of an isolator. So silicon photonics is very successful. It's growing very fast, but typically lasers need an isolator, and isolators can't really be integrated. So it's kind of the missing element. But there's a really good solution to it, and that involves using quantum dots. So I'll talk to that, and I really want to acknowledge the other collaborators at UCSB, as well as Intel, which has been doing all the reliability testing, and then University of Paris, Frederic Grilot's group's been doing all the isolator measurements, and Wang Chao did the theory for it. So the motivator, everyone knows, data traffic is increasing, so we have ever more transceivers, and we have ever larger amounts of data we need to store and transmit back and forth. And so the number of transceivers that are being sold every year is going up rapidly. And today it's all this color, which is 100 gigabit transceivers. But very quickly, this is all 400 gigabit transceivers. So before too long, next year there will be a significant number, significant fraction, should be 400 gigabit. Let's talk about how to do that and then what happens after that. So this push from 100 to 200 to 400 gigabit is not being really driven by the optics. It's being driven by the electronics, right? So switch chips are going from 12 terabits today to 25 to 50 terabits. And so that's really driving everything else. And so this is an article from Gazettabyte that just said, yeah, switch chips are what sets the pace that everybody else has to address. And what it's pushing is basically putting all the photonics very close to the silicon switch chip. So once you have 50 terabits of data, you can't send that very far. You're not going to have pluggables around the outside of a board. You're going to have all the optics co-packaged. And co-packaging is what really, to me, drives putting things on silicon. That's why our focus has been doing photonics on silicon. And so this 50 terabits probably not going to be 500 ports at 100 gigabit. That's just too many data points to handle. It's probably not even going to be 125, 400 gigabit ports. It's probably going to be about 64, 800 gigabit ports. So if you look at the radix of most of the switches, they're typically between 30 and 60. So maybe 64, 800 gigabit ports, or maybe 32, 1.6 terabit ports. So that's going to happen fairly quickly, just 3 years from now. So how do we do that? How do we achieve that? And certainly going faster data, going from 25 gigabaud to 50 gigabaud, that's happening today. Going from one fiber to multiple fibers or multiple wavelengths, CWDM4 is very common. And then going to higher levels of modulation complexity, PAM4, coherent, QAM, and so forth. And so that's what all the proposals are about. There's lots of different standards for how do you do 400 gigabit this way. The point being is that it really pushes integration, right? That if you end up having n wavelengths where n is 4, 8, or 16, p fibers where p is either 4, 8 probably, then you end up with 3 NP devices, and it's going to be like 100 devices that have to be integrated on a chip. And that's going to be the cost-effective winning solution. So that's what drives photonics, I think. So the problem with silicon, of course, is its indirect band gap. It's an incredibly inefficient emitter. 1 part in 10 to the 6th. That's pretty terrible. And the second problem we have to solve is that lasers are very reflection sensitive. So any of these advanced formats, certainly coherent, but almost every 100 gigabit transceiver today is reflection sensitive. So you typically need an isolator. And so people have these sets like this, where you've got a laser with a ball lens with a bulk isolator, and then it reflects down to a PIC layer down here. So you may have a really nice silicon photonic integrated circuit, but you got this big isolator and ball lens and all this crap. And here's another configuration similar to that. So the solution to that is you do the laser with 3.5 in silicon, and today it's been done heterogeneously, and I'll talk today about how to do it monolithically. And then the second thing is use quantum dot gain regions, and that makes them reflection insensitive, completely reflection insensitive, as I'll show you by the end. So this just summarizes those two things. What's being done today is putting 3.5 materials on top of SOI, and 3.5 is very efficient gain medium, and you can combine wavelengths from 5 microns to 400 nanometers gallium nitride. And of course, if it's visible wavelengths, you're not going to use silicon. We use silicon nitride. but most of these use silicon on insulator. And then I'll talk later about using quantum dot growth on silicon to make integrated lasers. So these are bonded devices. You bond all the gain regions at once. These are epitaxially grown. So I'll talk about both of those. This is just sort of our version of Moore's law. And so these are all the level of integration on indium phosphide. And Infinera in particular has really driven this. And this is the largest chip they've demonstrated to date. The red circles are integration on silicon. So it's now up to a few thousand devices. MIT's scanning device sits up there. And then the green triangles are integration on silicon with the laser integrated. And so that's progressed rapidly. Intel has a couple of products out, which now Juniper Orion has a product out. And this is about a 1.6 terabit switch up here. So that's, I'll talk a bit about this sort of thing, but I'll mainly focus on quantum dots, which is primitive in terms of integration, right? It's primarily one device, a laser by itself, or in this case, a laser with a modulator and a detector and an amplifier. So pretty primitive yet on that scale. So why go to 300 millimeters? Well, obviously, the wafer costs are cheaper, right? You can do 300 millimeter wafers. This is a wafer from AIM, so anyone can access that in a foundry process. The next foundry run is in May. Get lots of die back, and you get the advantages of CMOS process control. And that's in comparison to, say, an indium phosphide 50 millimeter wafer, which is smaller, more expensive, and doesn't have the process control. The other big advantage is low-loss waveguides, and I'll indicate one advantage of that in just a second. But silicon makes a really good waveguide material. It's bad because it's not an efficient light emitter, it's centrosymmetric, and it's reciprocal. So those are the disadvantages. So by heterogeneous integration, we can get all these benefits up here. We can solve all of these problems by integrating 3.5 for gain, or YIG for isolators, or going to quantum dots, or using piplin bonded on there, or gallium arsenide. And we've been doing gallium arsenide recently, and the advantage of putting gallium arsenide in silicon is you get very strong vertical confinement and very strong lateral confinement. So you can make very efficient things like second harmonic generation. So actually, the latest numbers are up here well over 1,000% per watt, and in principle, 1,000,000% per watt is possible. So I think the most efficient nonlinear devices will be made, again, heterogeneously bonding so as to get much tighter confinement than you can get just with epitaxially grown devices. So this is sort of where industry is today. I've got 2 slides from Intel just talking about doing this hybrid approach. I call it heterogeneous. They've always called it hybrid. But putting 3.5 on silicon to make lasers and getting the advantages of fabricating in a 300 millimeter facility, in this case in New Mexico, and then getting all the advantages of modern test equipment, modern packaging equipment that only exists at 300 millimeter, right? It doesn't exist at smaller wafer sizes. And there's a real nice invited paper here that describes that technology that just came out last month. And again, in terms of Intel's work, they launched their first product in 2016. They came out with 3 products in 2017. And last year, they really ramped it up. And as they say here, they're doing more than 1 million devices a year now at that. So last year, they did 1 million devices. They're accounting for significantly more this year. So that's the advantage, obviously, of using silicon, is the ability to scale up to very high volumes very quickly. The next talk after mine, Jim Harris's talk, is on LiDAR. So I put in one slide on our effort in terms of LiDAR. You'd like to have a 2-dimensional optical scanner. And so we're making, in this case, an FMCW approach to LiDAR. And so there's arrays of gratings. And as you change the wavelength, tunable laser on this side, and I'll talk about that next, the angle changes on this side. As you change the phase across here, then you make a scan beam in the other dimension. And here's a couple different devices. This is a 32-channel device. This is a 240-channel device. So lots of pads to control all these phase shifters in particular. And there's a picture of what those devices look like. This is how well they work. So this is scanning in 1 dimension for a 4-micron pitch or 2-micron pitch. Obviously, 2-micron pitch has a larger scanning angle. But again, you can scan very nicely. The side lobe level is pretty low. And then in the other dimension, you can see here the theta degree. You can tune, about 10 degrees the phase change across there. So the side lobe levels is fairly low. Works reasonably well. So that just came out in Optics Express about a month ago. So again, my last topic now in terms of heterogeneous, then I'll go to monolithic structures, is just looking at widely tunable lasers. And so now you can demonstrate widely tunable lasers that'll tune 100 nanometers, and that's what we used for that last scheme that I showed. But the advantage of silicon is that the losses are much lower. So if you look at all the indium phosphide tunable lasers, there's a lot out there. It's been done for 20 years now or 30 years now. But they're really limited in bandwidth to about 100 kilohertz sorts of numbers. But all the silicon groups, and there's probably 5 or 6 groups around the world making tunable lasers, are getting much lower line widths. This is 1 kilohertz. So this is down just a few hundred hertz line widths. And I'm fully confident that we'll get below 100 hertz this year. It's exactly what you expect because of the low loss gives you very high Q cavities, very low spontaneous emission noise. And so there's lots of groups that are doing this. And again, that's kind of inherent in the low loss of silicon, very high finesse cavities. So that's sort of heterogeneously what's going on in industry and some research results. But now I want to talk about epitaxially growing this. So rather than bonding devices on there, I want to grow the entire 300 millimeter wafer. And there's lots of reactors out there to grow 300 millimeters today. We work with IQE. We're making lasers on 300 millimeter from them. AIM has a reactor, and there's one more. I'm losing it. The problem when you grow is that there's dislocations, there's lattice mismatch. And because of dislocations, there's a real reliability problem here, dark line defect growth. There's antiphase domains. You're growing a polar gallium arsenide indium phosphide material on a non-polar silicon surface. And then again, the lack of an isolator is an issue. And so quantum dots, I think, solve all of those issues. And so traditionally, people like quantum dots because they're lower threshold, and indeed they are. Higher temperature operation, the highest temperature lasers are all quantum dot lasers. The lower diffusion length means you can make smaller devices less sensitive to surface recombination. So we make very small rings and get thresholds below milliamp as a result. And in particular, we got started in this because of the less sensitivity to defects. We can put literally thousands of dots in the area of one dislocation. And so you get some effect to the dislocation, but not so bad. You'll see more about that. But then the real big win is this fact, that with quantum dots, you can get lower line width enhancement factor. And that ends up giving you narrow line width lasers, which is good, but it also reduces your reflection sensitivity dramatically by orders of magnitude, actually. So here's some examples. So this is just a photograph of some lasers. These are the Stransky-Krasnov dots. So these are indium arsenide dots growing on gallium arsenide. And so here's LI curves, fairly reasonable thresholds, puts out 50 milliwatts. That's a typical wall plug efficiency. We've seen up to about 38% maximum. So they're reasonably good lasers. How did we get there? Because they weren't good lasers 2 years ago. Well, you have to deal with the antiphase domains. You have to deal with dislocations. And so you can deal with the antiphase domains in a few different approaches. So one is to work with miscut silicon, several degrees off. So everything until 2 years ago was based on off-cut silicon. Today, all the groups around the world are doing on-axis silicon. So it's fully integrable with conventional silicon. But how do you solve that then? One approach is to grow on these 111 surfaces. So if you look here, you can see these 111 surfaces. And the period here is typically about 200 nanometer period. And because of that, you get defects, but they all grow along those 111 planes, and they terminate at the top of those little points. They don't propagate up into this layer. So up here, you get actually low dislocation, zero antiphase domains. So that's an approach, and we've made lots of lasers that way. The other approach is growing gallium phosphide on silicon. And so again, it's a fairly thin layer, a few hundred nanometers gallium phosphide, but you can see all the antiphase domains. They all terminate within that first couple hundred nanometers. And again, it's a process NASP developed, and you can buy those wafers in 300 millimeter size. And the third approach that's being used is to grow aluminum gallium arsenide on top. And again, you can see here these antiphase domains. But again, within a few hundred nanometers, they've all terminated and gone away. The second thing we need to do is reduce the dislocations. And so again, here's just images of dislocations of our devices, gallium arsenide on silicon. And when we age those, you see this classic case of all those dislocations start to get all these loops, right? You get longer and longer effective length as these, because of photons being present in free carriers, these dislocations get longer and longer, larger volume, and the device gets worse. The device dies. And so here you can see this very dislocated layer up here, and that's the problem you have to do. So we solve that problem with two approaches. We do, or three approaches, basically two-step growth, a low temperature nucleation growth, a high temperature buffer growth, and then we do thermal annealing. We take it up and down 400 to 700 degrees C in an effort to drive all those dislocations to terminate on each other. And then the third approach is to have indium gallium arsenide superlattice layers and multiple layers of those. And those, again, are known to cause dislocations to terminate. And so here's an Ecke image of it, and you can't really see very well, but you can see a couple of these dislocations. And the density is about 7×10 to the 6th. So that's 100 times lower than where we started, and you'll see the impact on reliability is huge. So why are we and everybody else doing quantum dots when for the first 20 years of this field everyone grew quantum wells? Here's the answer. If you look at quantum wells in gallium arsenide, they look quite bright, quite good. You grow it on silicon and maybe the photoluminescence is 10%. You've lost 90% of the efficiency. That's a pretty standard result. In contrast with quantum dots, if you compare quantum dots in silicon, they're about the same. Now this image shows silicon being a little worse. I've got other images where it's exactly the same thing. We grow them side by side. There's no difference in PL from one to the other. So dots are really much brighter. They're much less sensitive to the dislocations. So again, here's this square right here contains all of these quantum dots, and there's the dislocation density right there. So there's literally thousands of dots per dislocation. And the carriers just don't diffuse far enough to see the dislocations. They get trapped in the local quantum dot. So here's the progress over time. Threshold current density. So that used to be 10 kiloamp per square centimeter. Now it's down below 100 amp per square centimeter. That's a really, really good, efficient laser. If you look at lifetime, the best quantum well lifetime has been, a few hundred hours, right? There should be one right here, I guess. That's the longest quantum well device. And that's, nothing in the last 18 years has been any better than that. In contrast, quantum dot devices keep getting better and better. And so lifetimes actually are now over 100 million in terms of room temperature lifetime. So it really does, there is a huge difference between quantum dots and quantum wells. There's no comparison. This is, again, some of Intel's data on our devices, but it just shows the impact. When you have 3×10 to the 8th dislocations, the lifetime is a few thousand hours. Get it down by 7×10 to the 7, you get up to a few years. You get down to 7×10 to the 6th, and you're up, pushing a 100-year lifetime. That's fine for room temperature, but not good enough for real reality. So you have to look at what happens when you age it at higher temperatures, and everything gets much worse. There's a real temperature acceleration factor here. And here's the answer. So that previous 7×10 to the 6th that was out to here at room temperature now dies in a few thousand hours. But as you do other things, we're calling Gen 4, Gen 5, they're all p-doped devices. They order 2 orders of magnitude better lifetime. And so this is kind of where we stand today, around 10-year lifetime in devices at high temperatures. So it's not good enough yet, but it's getting closer. Our quantum dot lasers on gallium arsenide have much better lifetimes. And again, there's no dislocations. So we're still dislocation limited in terms of its reliability. So it's improving, but it's not adequate yet for real commercial devices. Okay, so let's talk about quantum dots to remove the isolator. So we want to get rid of this bulk isolator. It's fairly expensive, obviously fairly big. Why are quantum dot lasers better? Why are they less reflection sensitive? Well, the critical field for instability in a laser, whether it's coherence collapse or other instabilities, goes like this line with enhancement factor to the 4th power. If alpha is small, we can neglect this. This is what matters. And typically quantum well devices have alphas of 2 to 4. With quantum dots, you can easily get them to under 1, and recently we've got it down to below 0.1. So at 0.1, you're literally 10 to the fourth times less sensitive than you'd expect for a normal quantum well device. And that's what you'll see. So theoretically, why is that? Well, quantum dots have, ideally a delta function gain spectrum. And then Kramers-Kronig says that the phase term should go through 0 right at that delta function. So if you look at calculated many-body calculations, and Wang Chao's been doing those for us, these are all individual dots of different sizes. So they're all fairly narrow, maybe 5 milli eV. But you put them all together, and they're broadened because not all the dots are the same size. What you calculate is that the phase change due to that is shown here. And what happens is on each side of that 0, you get large contributions to the phase terms in here. So out here you get large positive alpha, and in here you get negative alpha. And so what you have to do is shrink this up. And you can see this here. These again are, the black is our data on the improved devices when we work hard to make dots very uniform. And the blue and the red are Wang Chao's calculations. So if you go from this 50 milli eV photoluminescence line with down to 10, has a big impact on alpha. This is 20 MeV, this is 15, this is 10 MeV. So down here, alpha is 0. That's a reflection-sensitive device. And again, intuitively, what is coherence collapse? It's that you get a reflection back in the cavity, it changes the number of electrons, and in response to that, it changes the phase of the cavity. And if that cavity is long and far enough away and long enough Q, that's coherence collapse. But if alpha is 0, there's no phase change. You can change the reflections back all you want, and there's no phase change. So this is for undoped devices. You can get down to here. If you actually p-dope it, which is good for reliability, right? Good for high temperature gain, then you actually can get not just positive alpha, but negative alpha as well. And so that's why quantum dots are less reflection sensitive. So what's the data? The data's here. So look here. This is a quantum well laser. This is just the Fabry-Perot spectra of it. So this is the optical spectra. And up to about 1%, the laser looks kind of okay. But at 1%, then this laser has gone completely unstable. It's modulating essentially 100%. It's completely unstable at that point. So you'll see errors way back here, but in the optical spectra, you really see it about 1%. If you look at the noise out of the laser, again, noise at low frequencies, 0 to 10 gigahertz, you see nothing up to about 1% reflection, and then this whole laser is incredibly noisy. It's just gone completely unstable. And that's, again, very classic coherence collapse that's well known. If you look at the quantum dot, all the way up to basically 100% reflection, you don't see anything. And if you look at the noise in here, again, you don't see anything up to there. So there's a huge difference between quantum wells and quantum dots, and it's just what you'd expect. So what this 100% is light coming out of the facet is coupled into a fiber. 90% is sent to a reflector, and it's 100% rep reflector sending back into the laser. And if you look at the high points up here, you can see these curves are curving a bit. That's because at this level, you're heating the laser. There's so much reflection back into the laser, it's heating up and shifting. You can see the same thing in the quantum well device as well. So, I mean, that's a big reflection, not a small reflection. It's a big reflection. If you look at the error rate, which is what matters, the quantum well device at 0.02% has a reasonable eye diagram. At 2%, it's a very, very noisy eye diagram, right? It's really gotten a lot worse. And if you look at the bit error rate for just back-to-back versus 0.02%, so right, that's 2 10 to the minus 4 reflection. There's already been a degradation, right? Called this way, a couple of dB degradation. And if you get to 2%, where this thing is really noisy, you've gone all the way up here to 10 to the 4 error rate. So big effects, small effects at 10 to the minus 4, big effects at 2%. In contrast, the comparison here is a little different. Back-to-back is the squares, 100% reflection are the triangles. There's no change in bit error rate at all. This is if you put it through fiber just to see if there's a transmission effect. And so back-to-back is the squares, and 100% reflection is the triangles. So again, no effect. So you really don't need an isolator for quantum dot laser. That's the point, if you make them uniform enough. And so in our earlier results, we did not have the narrow distribution of dots, and indeed actually you do see a larger alpha, and you see more reflection sensitivity. So here's an example now. I'll show two systems experiments of what one can do. This is some result from Hewlett-Packard. So these are quantum dot gain regions that are bonded now, not epitaxial. They're doing a bonded approach, and so it's the work going on here and at UC Santa Barbara. So here's the laser. There's the HR coating on this side from a grating reflector DBR, a low reflection DBR on the other side, gain region in the middle, and then a series of modulators in the output of different diameters, right? So each one is aligned to a different wavelength. So this mode-locked laser puts out a bunch of different mode-locked lines here, and you space those at exactly, say, 100 gigahertz, whatever the frequency of your transmission system is going to be. And then looking at the output, then this is their eye diagrams, and across 14 channels, they measured error-free operation of that. And this shows the LI curves, and again, pretty nice high temperature performance, right? 100 degrees C, there really isn't any change in the slope efficiency here, and it still lasers quite nicely with, 5 or 6 milliwatts output power. So that's one example. You can go even further, and so this is some work we've done at UCSB. In this case now, we're not making uniform quantum dots, we're intentionally chirping the quantum dots. And the reason we're chirping them is we're trying to get a broad gain region, broader than you'd get naturally from quantum dots. And so this shows the spectrum of layers of quantum dots in there. So as we change the growth characteristics, we can change the different layers to have peaks at different wavelengths. And that gives us overall a wider gain spectrum. So now, rather than trying to get down to 20 MeV or 10 MeV, we're now broadening it to 70 MeV. And so it's just a classic colliding pulse mode-locked laser. So you've got a satchel absorber in the cavity. And so this pulse with its reflection gives you passive mode locking in that device. And this is the spectrum. So it's hard to see the lines at this resolution, but within 3 dB of the peak, you've got 58 lines, each at 20 gigahertz spacing. And we put 32 gigabaud PAM4 on each of those. And so then there's 64 channels that get transmitted within the FEC limit. So as you go across that, every 20 gigahertz, there's another line here. And so each of these circles is the error rate on that channel. And each of them is then carrying PAM4. So when you put that all together, that ends up being about 4 terabits of transmission. So it's a nice way to go beyond where we are today, say 400, 800 gigabit. The HP approach is actually very good for 800 gigabit. This is what to do after that. If you need to get to 1.6 terabit, 3 terabit, or beyond. So to summarize, there's lots of pretty high performance picks being made. Intel is the first to ramp to high volume. There are over 1 million units per year. There's about 10 devices integrated on there. Multiple lasers, typically 4 lasers, 4 modulators, 4 monitor diodes, a receiver which has 4 detectors on it. Acacia is dominating in the coherent telecom space. I didn't talk about their results, but this is at 1310 and this is 1310. That's at 1550. But again, high volume silicon photonic solutions. So, lasers on silicon are here today. They're commercialized in this million device per year scale on 300 millimeter substrates. Epitaxial is progressing. It's not reliable enough. No one's commercializing that yet, but it's moving pretty fast. So the highest level we have today is about 1,500 elements on a chip. That's Juniper's 1.5 or 6 terabit result. We've demonstrated UCSB 2.5 terabits on a chip. And then I pointed out that if you make uniform quantum dots, you can make the lambda enhancement factor 0 or slightly positive or negative. And consequently, then you don't end up needing optical isolators, even with high levels of reflection. And it's just exactly what you'd expect from theory. So I want to thank the students who did all the work, in particular Frederick Rouleau, who did all the isolator measurements, and Intel for doing the reliability measurements, and DARPA and ARPA-E for funding. Thank you.